Hi, everybody. Today we are covering part of chapter 3 in our electric circuits text. The topic of chapter 3 is simple resistive circuits. This first lecture covers sections 3.1 through approximately 3.5. And what we're really getting up to is using the ideas of resistance in resistors in parallel and in series in order to calculate equivalent resistors or equivalent resistance, voltage in certain components and current in certain components. So that's where we're kind of aiming at by the end of section 3.5, the end of this lecture. Then the next lecture for this chapter will cover 3.6 and 3.7, which talks a little bit about measuring resistance using an apparatus called a Wheatstone bridge, which a Wheatstone bridge is just a particular configuration of resistors that allows you to precisely measure the resistance of an unknown resistor. So there are different types of apparati that do this sort of thing, but a Wheatstone bridge is pretty well known, very accurate, and well accepted in industry. So having said that, let's take a peek at the PowerPoint for this particular first part of the chapter, sections 3.1 through 3.5. All right, so the purpose of today and the purpose of chapter 3 is to know how to identify components connected in series and in parallel, which is what we'll talk about at length in just a few minutes, to be able to find equivalent resistors of series connected and parallel connected resistors, which as follows, and to be able to recognize circuits when voltage division occurs, and to know how to use voltage division to analyze such circuits. And finally, to be able to recognize circuits when current division occurs, and to know how to use current division to analyze these circuits. So at the bottom of chapter 3 on our Moodle page, I have written a series of important formulas, and these will be available to you on our Moodle page, and they go along with what we've just talked about. So by the end of the lecture today, you'll be able to work with that formula sheet to do the problems in this chapter. All right, so the first thing is we talk about what does it mean to be connected in series? What does it mean to be connected in parallel? The circuit that's shown on your screen right now is an example of 7 resistors connected in series. And the way that you identify this is if the nodes are on the entrance and the exit, or entering and leaving each resistor. In other words, if the connectors are connected end to end. So if you have connectors that are connected end to end like this, every one of them will have the same current. And you can determine that using Kirchhoff's current law because of the nodes, because everything entering and leaving the node has to be the same or equal to 0 if you subtract them, but everything entering has to leave as far as current goes. So the current across each of these resistors is going to be the same. So when we talk about that, we can say that a resistor in series does not divide the current, but the resistors in series like this will divide voltage, which we'll get into in just a couple of minutes. All right, so basically when we have simple resistive circuits like this, we find using Kirchhoff's voltage law that the equivalent resistor, in other words, if we were to replace these 7 resistors in this particular circuit with so to find an equivalent resistor, it's just the arithmetic sum of all 7 resistors in this case. So the basic punchline of this, or the fundamental equation, is that resistors in series add arithmetically, and the equivalent resistor is always larger than the rest of the resistors in the group, right? Because resistors are always positive, therefore the value of their sum has to be greater. Okay, so on your screen now is an example of some resistors in series and some resistors in parallel. If you look at the current source right here, you'll see that the current would flow from this node through the 10, through the 40, and through the 20. And that means because the 10, the 40, and the 20 are connected end to end, that they are in series. Now, the others, the 12, the 20, and the 180 are different, and that's what we're going to talk about next. So if we first of all talk about what's the equivalent resistor of the series connected resistors, 10 plus 40 plus 20 is 70 ohms. And so in this loop on the left of the current source, the series resistors have an equivalent resistor of 70 ohms. So in other words, you could write this side in equivalent way of just the current source and a single equivalent resistor that measures 70 ohms. All right. Here we go. It's kind of skipping around a little bit today. So if we talk about voltage division, we can find the voltage drop across any one of these groups. Now, there's a formula that governs voltage division or the voltage drop. And what it basically means that the current stays the same across resistors, but the voltage across each resistor in series is going to be different. So if you choose the voltage across resistor 4 over here, there's some work up in the book, and there's some a little bit more formulas on the formula sheet that I've given you. But basically, if you take the current source and multiply it by that resistor, then multiply it by this, by this, I don't know how to put this. This is an expression for the voltage source. Okay, because why? Because voltage is equal to current times resistance. That means that current is equal to voltage. V is equal to IR. Therefore, I is equal to V over R. This is the equivalent voltage. So in other words, we have that the voltage in 4 is going to be the resistance in 4 over the equivalent resistance times the voltage of the source. V times some sort of a fraction of what the fraction of R4 is over the equivalent resistance of the circuit. This is all derivable using V equals IR and the statement that we just came up with for the voltage division or for resistors in series. All right, so this statement, a simple resistive circuit, in order to use voltage division to analyze a circuit, there must be a voltage source and 2 or more resistors all connected in series. Is that true or false? Well, the answer is not necessarily. In other words, you could have a current source and you could do that as well. Okay, the next type of a configuration that we have for resistors that are not in series, resistors can also be in parallel. What that means is when you examine a node, that the head and the tail of the resistor do not, it doesn't go through one and then go through the other. It goes through them essentially by dividing the current. So what that means is instead of being connected end to end, the resistors are connected at both ends. Okay, so the difference here is you can see that we have a connector going from one end of the resistor to the other, but that does not lead us into another resistor. We have to go through some other piece of the circuit before we get to the next resistor and so forth. Okay, now here, if you look at Kirchhoff's voltage law, you'll find that each one of these resistors will have the same voltage. So for resistors connected in parallel, voltage 1 will equal voltage 2, will equal voltage 3, will equal voltage 4. But in this particular case, the current is not going to be the same. The current is actually going to divide. So for resistors in series, voltage is divided. For resistors in parallel, the current is divided. All right, so how do we come up with an equivalent resistor for a circuit like this? Well, the way that your authors do it, and I think it's pretty great, they start at the end and they take R3 and R2 and they do Kirchhoff's current law, and then they do they take a look at the two resistors and what they come up, and then they kind of work their way back. So they take these and come up with an equivalent resistor, then take it with this R3 plus R4 equivalent in parallel with R2, and then R2, 3, 4 in parallel equivalent with R equivalent in parallel with R1. And what you come up with is you have a situation where 1 over the equivalent resistance is equal to 1 over the resistance of the first plus the resistance of the second plus the resistance of the third plus the resistance of the fourth. So in other words, this is a harmonic average. It's not an arithmetic sum. It's a harmonic sum. And what that means is that the equivalent resistance of all of those resistors is going to be smaller than the resistance of the 4. So putting in configurations like this will actually decrease the resistance equivalent in the circuit. All right, so here the question is asked, which of these resistors are connected in parallel? Well, we already know that the 10, the 40, and the 20 over here on the left are connected in series because it goes one through the other, one through the other. If we look at these two, we can see these are not connected end to end. They're connected. They're not connected in series. They're connected in parallel. So the 20 and the 180 are connected in parallel. It turns out that the 20 and the 180 are connected in parallel with the 12 and also with the equivalent resistor over here. But the answer to the question is the 20 and the 180 ohm resistors are connected in parallel. Okay, so then the fun begins when we start looking at finding equivalent resistors in parallel connected in the parallel connected resistors. So we're looking at the 20 and the 180. So the equivalent resistor 1 over Req is going to be 1 over 20 plus 1 over 180. And if you do the math on that, you'll find out that it's 18 ohms. It's important to note that 18 ohms is less than 20 and is less than 180. And that's a requirement for a correct calculation done on parallel resistors. Okay, so now we're going to tie the idea of current division into parallel resistors. So like I had said earlier, if you have parallel resistors, they divide the current. If you have series resistors, they divide the voltage. So here we have a current, I sub S, I from the source, that's going to be divided among R1, R2, R3, and R4. And R1 is going to carry I1, R2 is going to carry I2, and so forth up through I3, up through I4. All right, so if we want to find I sub 3, that's going to be, remember once again, V is equal to IR, so I is equal to V over R. So here we're talking about the voltage at the source divided by R3, which becomes the R equivalent times I sub S over R3, or that ratio R equivalent over R3 times IS. Now it's interesting to note that R equivalent is going to be that smaller number, not necessarily, well, yeah, it's going to be smaller than R3. So R equivalent is going to be smaller than everything in the circuit. Okay, so the next slide, the equivalent resistance of a group of parallel connect resistors is smaller than the resistance of the smaller resistor in the group. And as we just went through the math, it is indeed true. All right, now this little table, I'm not sure if I love it or not, but it is a good way of keeping straight the difference between series and parallel. So you see that if you have a voltage source or a current source, we can think about if a voltage source goes along with a voltage division, a current source goes along with a current division. that the property that we would think about with a voltage source is resistance. With a current source, we would think about conductance, which of course is 1 over the resistance. For voltage sources, we use Kirchhoff's voltage law. Current source, Kirchhoff's current law. Voltage sources, we're talking about a series connection and voltage division. That's really the only part of this chart that I like. And then for current sources, we're talking about parallel connections and current division. Okay, and then we can talk about a short circuit or an open circuit. So once again, not real crazy about that chart, but it does, the part that I do like that it brings up is that series connections divide voltage, parallel connections divide current. All right, so to review, series connected components, resistors in series add arithmetically so that the equivalent circuit is just equal to the sum of the individual resistors in that circuit. Similarly, if you have a voltage division, lets you know that you find the voltage across one component, then you know you can use this equation that the voltage across an individual resistor is equal to the voltage of the source divided by, multiplied by the individual resistor divided by that equivalent resistance of the entire circuit. Okay, similarly, if you have parallel connections, in other words, not connected end to end, but you have the other type of a connector that it's not an arithmetic add, but it's an add of the reciprocals equals the reciprocal of the equivalent. Okay, so we can still come up with an R equivalent, which is the reciprocal of this expression. So that goes here. R sub x is whatever component we're looking at. The current going through that component, that resistor in this case, is equal to I of the source times this ratio. All right. So if we take a look at some simple resistive circuits, what we're going to do here is to look at a circuit where some of the resistors are in parallel and some of the resistors are in series. It's commonly accepted, but the symbology that the symbols that your authors use, if they are in series, if the resistors are in series, you add. So they just use a plus sign. If the resistors are in parallel, they use parallel, just 2 parallel bars, and they do the math. 1 over this plus 1 over this equals 1 over this. Okay, so that's how they arrive at those numbers. But so we come up with, we start over here, we have a 6 and a 10 in series. That's 16. Okay, then after we do that, we have the 16 in parallel with the 64. So that's that. And we found the equivalent of this loop. Okay, then we have that 12 this is equivalent is 12.8. So we have a 7.2 in series with the 7.2, which is the equivalent of these 3 resistors. So we add those together here, just arithmetic add because it's series. And then finally, we have that in parallel with the 30. And so we do this calculation. Okay, and so with this is actually the equivalent in the entire circuit. And so we can then use Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law to determine the voltages and currents in those components. All right, so here's another, find V sub 0. We're looking at, here's an R sub L, here's our voltage. Okay, so I have a current source and we have we have 2 resistors in parallel, R sub L and 75 kilo ohm. Don't forget, change it to ohms. And then that equivalent circuit will be in series with the 25. So we find these 2 in parallel, and then we find this in series with that equivalent. Okay, so the question is, if we want the load resistor to have very little effect on the designated no load voltage, the load resistor value should be much smaller. No, because in parallel, that is, you want it to be much larger because it's 1 over. All right, and here's just another example of a simple resistance circuit. We have a 10 and a 50 in series. And they always tend to do this. They always tend to start at the end, which is really kind of a handy, it's not necessary, but in general, it's a good technique. Come away from the voltage or the current source and construct the circuit from there. So these two are in series, so they are 60. Then you have 60 in parallel with 30, and then that equivalent is in parallel with a 20. So the equivalent of this entire circuit is 10 ohms. Then you can use voltage division, Ohm's law, current division, Ohm's law, and voltage division to solve for the rest of what's going on in that circuit. All right, everybody. So like I said, I will do another lecture for this this chapter covering the last two sections, sections 3.6 and 3.7. I will post the important formulas for chapter 3, and I'll look forward to hearing from you if and when you have any questions or problems. Have a great day.